Okay, so Omid is
Hello,
going to present his extended abstract. Please go ahead.
hello everyone. I'm Omid Tarkhaneh, Department of Scientific Computing, Memorial University, and this presentation is about deep convolutional neural network for molecular energy prediction. Molecular energy prediction is of great importance to understand the chemical and biological process. Thanks to the computer modeling, we are provided with some potential energy surface and the chemical properties, which help us to predict the potential energy surfaces. There are some classical methods for this problem, which is density, functional theory, coupled clusters. But there is a big issue with them, and these methods are computationally expensive. We utilize convolutional neural network here in order to predict heart rate energy. Our problem, in fact, is kind of a linear regression problem, and as our target are continuous values. And as you know, the linear regression for a single one, we have different things like dependent variable, independent, intercept, and then slope. Our problem is, in fact, it's kind of a multiple linear regression as we have different independent variables. We have utilized kind of a repository called Retrivium, which consists of over 17 million data entries, each in terms of a kind of a CML file or XML file. We extracted data from this, a fraction of these CML files, and tried to create a kind of a matrix based on them. The database structure consists mainly of different, like carbon, nitrogen, oxygen, and sulfurs. And the matrix that you can see here is the matrix that we proposed. A and B and C here indicates to the atom properties, which are atom number, atom type, valence, and here the denote to the distances between each pairs of the atom, which is just calculated based on the Euclidean distance. Here x1, y1, z1 indicates to the position of atom 1, and x2, y2, and z2 denotes to the position of atom 2. So after creating our data sets, we have just also have kind of exploratory data analysis on the data, and this is just the reduced. We reduced the dimension from 29 to 2, and this is the whole shape of our data sample. This is fraction of our data, not the whole 70 million of those data. And we utilize one of the well-known architecture for this, which is VGG, which is introduced in an ImageNet challenge 2014. We try to fine-tune the parameter based on our case study, and we utilize different layers like two-dimensional convolution, max pooling, and our input shape was kind of 29 times 29 matrices. And the whole number of parameters were over 2 million. This is also the achieved parameter that we tuned here. We utilize different filter size, and we use regularizers like L1 and L2, and different other parameters, which are just achieved based on the experiments. And in our data set, we meet some issues. We see that there are some instances that are hard to learn. We try to find a kind of data augmentation method in order to double the size and enhance those hard to learn instances for the model. And fortunately, we have achieved kind of reasonable and promising results. We also use different metrics. Our metrics is mean squared error as a loss and mean absolute error for our metrics. And we utilize R-squared in order to show the coefficient of determination. So our goal was to decrease the residual, I mean the distance between the observed value and the predicted line. And fortunately, we have received such as the result that you can see here in this table, which are somehow promising, but still there is a lot of rooms and a lot of steps remains to take. Here we achieved 0.87 in terms of the test, and this figure is showing the difference in percentage of error percentage in differences. Here is showing that the range of the majority of data point is between -2 and 2, which are somehow promising. And here in this figure that you can see that there is still some residuals. I mean the error in our data, but we are just trying to enhance the model as much as possible. And for the conclusion and future work, I can say that our results are somehow promising, but there is a lot of rooms remains. As the molecule can be considered as a kind of a graph. So for non-Euclidean spaces, graph neural network can be considered instead of using CNN, which is used here. And another future work can be trying different augmentation methods, such as rotating the input matrices and any other things that can be used as an augmentation. And another thing is exploring other molecule metrics available in Retrivium database. Last but not least, I want to acknowledge and thanks to my supervisor and great team that I'm working with. And these references, and thanks for listening. Oh, I just finished on time.
Good. Thank you, Omid. All right, questions? Okay, go ahead, Renata.
Thank you. Thank you, Omid. I have one quick question. This matrix that you presented and that you from your file, XML file, is something that you've thought about it, or is something that you've been using in your field? It's not familiar.
This matrix is something that comes on our mind in order to create based on those CML files. And as you can see, we utilize different attributes, and our distances are depicted based on the Euclidean distance. I don't know that I understand your question.
Oh, it was something, if it's you that thought about the structure, or is something from related work, or it's...
No, it's not from any related work. It's just something that that we designed for this problem.
Oh, okay, thank you. Thank you.
Yeah, you're welcome.
I have a question. Can you hear me?
Yeah.
Is there a particular reason that you chose to use a CNN model for this problem? Is there any sort of structure in the inputs that the CNN can exploit, similarly to the way it would exploit structure in an image?
Yeah, our in fact matrix is something that here we didn't use all of the atom attributes because, for example, most of the researchers that I have seen work in terms of chemistry using deep learning, they use deep graph neural networks. But here we utilize the CNN, which I didn't, to the best of my knowledge, didn't see anyone that used CNN in order to predict the energy. I say this to the best of my knowledge, but the reason that we use here, because not all of the features that we use is the molecule features. So some of them are Cartesian positions, and that's why we use CNN here.
Thank you.
You're welcome.
All right. Thank you very much, Omid.